Every steel design you will ever do begins with two questions. What steel is this and what shape is it? That is the whole of this lesson. The grade tells you how strong the steel is, the section tells you how well that strength is arranged, and design is simply the art of matching the two. None of this is difficult, but almost all of it is examined by memory, so read it slowly and keep a pencil in your hand. Steel is not chosen because it is strong. Concrete is strong too. Steel is chosen because of how much strength it gives for how little weight and because it behaves honestly when you overload it. 6 things count in its favor. Its strength to weight ratio is the highest of the common building materials, so members are slender, spans are longer, and the foundations carry less. It is ductile, it stretches visibly before it breaks, so the structure warns you. It is made in a factory, so its properties are certified, not hoped for. It is fabricated off-site and bolted up in days. It can be strengthened, extended, or taken down and re-erected somewhere else. And at the end of its life, it has scrap value, not disposal cost. Now, the other side, steel corrodes, so painting and maintenance run for the whole life of the building. It loses strength sharply in fire, so fire protection is not optional. Slenderness is the price of lightness, so every compression member must be checked for buckling. Repeated loading can fatigue it and fail it below its static strength, and it costs more at the start and needs trained hands at the connections. So steel is the natural choice where speed, long spans, or lightweight decide the design, and the natural second choice where fire, corrosion, or low first cost decide it. There was a time when people believed uncased iron was fireproof. It is not. Heated iron distorts badly and becomes unfit. Watch what heat actually does. Plot the strength of steel as a proportion of its unheated yield stress. Up to about 250 degrees it holds. It even rises a little and then it falls away. By 700 degrees there is very little left. Steel does not burn, it simply stops being strong. So how do we protect it? The oldest way is to encase it in concrete or brickwork. It works, but it adds about 10% to the dead load. It needs extra labor, it can mean a heavier foundation, and it cannot be used at all on roof trusses, lattice girders, or space frames. So lighter materials came in: vermiculite, gypsum, and perlite, supplied as dry sheets or as plaster. Light, quick, and no formwork. There is a modern method where the column is made hollow and cold water is circulated through it. And there is a special paint that froths when it gets hot, and the froth itself becomes a protective layer, and the cheapest protection of all costs nothing. At the planning stage, simply put the columns far from the sources of heat. 3 casings to know and to sketch. Solid casing, the section buried in a block. Hollow casing, a box around it with an air gap. Profile casing, the protection following the shape of the section. 3 more things steel is vulnerable to, and each is examined in its own right. Fatigue, pulsating loads at high frequency cause extreme variations of stress and can even reverse it. Repeat that over enough cycles and the member weakens. A fatigue failure almost always begins as one very small crack made by a very high stress at a single point, which is why fatigue is dangerous exactly where stress concentrates. It matters most in the tension members of bridge trusses, where the joints should be made with HSFG bolts. In ordinary building construction, it is not a serious concern. Brittle fracture steel is ductile. It can stretch by about 1/5 of its original length before it fails. But sometimes it fails suddenly with almost no extension at all. 2 causes: steel is ductile when warm but brittle below a critical temperature, and a zone of stress concentration will develop a brittle fracture. Ductile failure warns you, brittle failure does not. That is precisely why IS 2062 gives you subgrades. And corrosion: unprotected steel rusts readily and smoke, soot, seawater, and acidic or alkaline vapors all speed it up. We protect it with paint, with metal coatings like galvanizing and zinc spraying, with aluminium or zinc metal spray, with electroplating for small items like fasteners, or with a plastic sheathing. But here is the part that decides whether any of it works. The surface must be cleaned thoroughly first. For structural steelwork, that means blast cleaning, Tiny abrasive iron particles fired at the steel by compressed air. Paint on a dirty surface is wasted paint. The bond is the protection. A drawing that says steel beam has specified nothing at all. What a drawing must say is the grade. An Indian structural steel is graded by S 2062. The grade is written as the letter E followed by the yield stress in newtons per square millimeter. So E250 is steel with a yield stress of 250, but strength always comes as a pair. For E250, the ultimate tensile stress is 410. Yielding is checked against the first number, rupture against the second, so a complete answer gives both. You will also meet subgrades A, B, R, B0 and C. These do not change the strength at all. They set how tough the steel must remain when it is cold. E250BR and E250C are the same strength. They are certified for different duty. And here is the part almost everyone leaves out. The yield stress falls as the material gets thicker. Thick plate cools more slowly as it is rolled and it finishes weaker. For E250, the full 250 holds up to about 20 millimeters. Beyond that, it steps down. If a question hands you a thick section, go and find the reduced value. Using the wrong one puts your answer on the unsafe side. Pull a specimen of steel until it breaks. Plot the stress against the strain. And every number you will ever design with appears on that one graph. At first, the line is perfectly straight. Stress is proportional to strain. Hooke's law applies, and the slope of that line is the modulus of elasticity. The straight part ends at A, the limit of proportionality. Just past it, the steel gives way. B is the upper yield point, and then the curve drops to C, the lower yield point. Mark C carefully. C is the value design actually uses. Now watch what happens next, because this is the property that makes steel worth building with. The specimen keeps stretching, and the stress does not rise at all. That flat stretch is the yield plateau. It is ductility made visible. The steel is telling you at constant load that it is in trouble. After the plateau, it toughens again, strain hardening, and climbs to D, the ultimate stress. That is the highest stress the specimen ever carries. And then something that surprises students, the curve comes down. The bar necks, its cross-section thins locally so the load it can hold falls away. It finally breaks at E at a stress lower than the ultimate 4 stages, and name them if you're asked. Elastic, yielding, strain, hardening, necking. One last thing before we move on. That curve is awkward to calculate with. So for design, we simplify it. A straight elastic line, then a flat plateau running on. That throws away strain hardening completely, which means it ignores real strength the steel actually has. So the simplification is always on the safe side. Remember that shape. The whole of plastic analysis is built on it. Everything you have just seen assumed mild steel. Now look at what high-strength steel does. There is no drop, there is no plateau, the curve simply bends over and keeps going. So where is the yield point? There isn't one, there is nothing on that curve to point at. So the yield stress is not observed, it is defined by construction. Here is how. On the strain axis, mark a strain of 0.2%, that is a strain of 0.002. From that point, draw a line parallel to the straight elastic part of the curve. Find where that line cuts the curve, read across to the stress axis. That stress is the 0.2% proof stress, and it is taken as the yield stress for design. Why 0.2? Because it is the stress that leaves a permanent set of 0.2% when you unload, small enough to be harmless in a structure, large enough to measure honestly in a laboratory, stronger steel, but far less warning before it fails. Alongside the strengths, steel has a set of elastic constants, and these come from the code, not from the test certificate. The modulus of elasticity is 2.05 times 10 to the power 5 newtons per square millimeter, and your book adds 3 words worth remembering, irrespective of the type of steel. The modulus of rigidity 0.769 times 10 to the power 5, Poisson's ratio 0.3. The coefficient of thermal expansion 12 times 10 to the power minus 6 per degree Celsius, and the unit mass 7,850 kilograms per cubic meter. Now the sentence that carries the mark, not one of those 5 changes with the grade. E450 has exactly the same modulus of elasticity as E250, the same rigidity, the same Poisson's ratio, the same density. Only the yield and ultimate stresses change. Watch what that means. 2 identical beams, same section, same span, same load. One is E250, one is E410. Deflection depends on E and on I. It does not contain the yield stress anywhere. So they deflect by exactly the same amount. A stronger grade buys you strength. It buys you no stiffness at all. If a beam fails on deflection, changing the grade will not save you. You must change the section. Steel does not arrive as a material you shape. It arrives already rolled into standard sections, and you choose from a catalog. The workhorse is the I section: junior beam, light beam, medium weight beam, wide flange beam, and the heavy or column beam. These carry your beams and your columns. Next, the channel, a back with 2 flanges on one side, purlins, bracings, and built-up columns, then angles, equal and unequal. The whole world of trusses is built from angles, ties, and struts, T's for truss cords and connection pieces, round and square bars for sag rods, tie rods and bracing, flats and plates for gussets, base plates and splices, and finally the hollow sections, circular, square, and rectangular. These deserve a segment of their own, and they will get one. Notice what decides the choice, not appearance, but the action the member carries. I sections for bending, angles and tubes for axial force, plates for connections. Ask for steel at a stockyard and nobody can serve you. Steel does not leave the mill as a material, it leaves as a product, a definite form with a definite name ordered by a definite description. Almost all of it is hot rolled. A glowing billet is passed back and forth between rollers that squeeze it thinner and longer at every pass until it takes the shape the mill was set for. That is why we say rolled sections. Some products are made the other way. Cold formed, a thin sheet is bent to shape at room temperature without heating. It gives you light gauge sections, much thinner than anything that can be hot rolled. Everything the mill makes falls into 4 families: flat, long, hollow, and special, plus the fasteners that hold them together. Learn the families and the whole product list stops being a list to memorize. First, the flat family, and here students lose marks because the 4 members of it look alike on paper and are not alike at all. A plate is the thick one. It is what you cut gusset plates from, base plates under columns, splice plates at a joint, and the web and flanges of a girder you build up yourself. Anywhere steel has to be shaped to a joint rather than run as a member, it is plate. A sheet is thinner. Sheet is a covering material, not a load-carrying one, roofing, cladding, ducting, casing. A strip is a narrow sheet and it is supplied in coils rather than flat lengths because it is thin enough to bend without damage. Strip is the raw material for cold-formed sections, and a flat is a narrow bar of rectangular section 50 by 6, 60 by 8, and so on. Ties, lacing bars, grillwork, straps. So, plate for joints, sheet for covering, strip for forming, flat for small members. 4 words, 4 jobs. The long family is anything supplied as a length of constant section. Bars, round or square, named simply by their diameter or their side. Sag rods, tie rods, bracing, anchor bolts, and the rolled structural sections you already know, the I sections, channels, angles, and T's. These are the members themselves, the beams, the columns, the truss members. Then the hollow family, circular hollow sections, steel tubes under S1161 supplied in light, medium, and heavy classes, and square and rectangular hollow sections under S4923. Remember why these matter. A hollow section has the same radius of gyration in every direction, so there is no weak axis for a strut to buckle about. For compression members, hollow wins, and it wins by a lot. Now the products that are made from the others, take a plain sheet and lay it across a span. It sags, it has almost no stiffness of its own. Now press waves into it. Nothing has been added, not 1 gram of steel, but the waves push material away from the middle plane and the same sheet now spans. That is a corrugated sheet, and that is the whole idea behind it. Galvanize it and you have the roofing sheet on half the sheds in the country. Expanded metal is made by slitting a sheet in a staggered pattern and then stretching it open. No steel is removed, so there is no waste. It gives you mesh for plaster reinforcement, fencing, safety screens, and walkway flooring, and finally the fasteners, because members are useless until they are joined. Rivets now obsolete in practice, but still in your syllabus and still in your question paper. Bolts, ordinary black bolts, and high strength friction grip bolts that clamp the plates so hard the joint carries by friction, with nuts and washers to suit. One last habit: a steel product is never ordered by name alone. It is ordered by form, dimensions, grade, and code. Plate 500 by 300 by 12 millimeters, E250 to S2062. Say all four and the right steel arrives. Here is a piece of fabrication that looks like a trick and is not. Take an ordinary I section. Run an automatic flame cutting machine along the web, not straight but in a zigzag. The beam falls into two halves, each with a row of teeth. Now slide one half along until the teeth of the two parts match up. Weld them together. Look at what you have: a deeper beam from exactly the same piece of steel, not 1 gram added. And because bending resistance depends so strongly on depth, that beam is now substantially stronger in bending than the one you started with. This is called a castellated beam, and the hexagonal openings left through the web are not waste. Services run through them, and you can go further. Insert plates between the teeth before welding, and the beam grows deeper still. Same idea as the tube in a different disguise. Put the steel where the work is, and the work in bending is at the top and the bottom. Sometimes no rolled section in the table is enough. Then you build one. The simplest way is to weld cover plates onto a rolled section. Plates on the flanges of an I section, or across a pair of channels, or across a double I section. You're adding steel exactly where bending needs it. The second way is to combine two different sections so that each resists load in a different direction. The classic example is a crane girder, an I section carrying the vertical load, with a channel on its top flange to take the horizontal surge of the crane. The third way is to take two separate sections and tie them together so they act as one member. If you connect them with diagonal bars, it is a laced member. If you connect them with short plates like the rungs of a ladder, it is a battened member. And the fourth way is to build the member entirely from plates welded together. I, H, or box shapes, these are plate girders, and they are what you use for heavy loads and long spans where no rolled section will do. Thin plates and strips do not have to be rolled hot. They can be folded cold at room temperature, and that gives a whole family of light gauge shapes: the lipped angle, the plane angle, the channel, and the inward turned up channel, the closed joint tube, the T and the Z. Light, cheap, and ideal for purlins and sheeting rails. A word on structural steel tubes: they are used for trusses, for domes, and as scaffolding. They run from 15 millimeters internal diameter up to 150, and for each internal diameter you can get 3 different thicknesses. The large ones make excellent columns. And finally, the rest of the family. Square bars ISSQ from 5 millimeters up to 200, round bars SRO. The same range used as reinforcement in RCC and in trusses and sheds. High tensile steel rods for prestressed concrete, steel rails for railways and for crane rails, and corrugated galvanized iron sheets roofing the workshops, godowns, and sheds of the whole country. One list, one logic. Every one of them is steel put into the shape that suits the job. An I section has two flanges joined by a web with a root fillet where they meet. Its dimensions are the overall depth D, the flange width BF, the flange thickness TF, and the web thickness TW. Two axes matter. Z running through the web is the strong axis. Y is the weak one. Every I section is weaker about YY, and that single fact drives column design, the lateral support of beams, and the whole idea of lacing. Now, why is the section shaped like that at all? Two numbers answer it. In an I section, about 80% of the bending moment is carried by the flanges, and about 95% of the shear is carried by the web. That is the whole design of the shape. Bending wants material as far from the center as it can get, so the flanges are wide, thick, and pushed to the extremes. Shear is carried near the middle, so the web is deep and it can afford to be thin, and it tells you where to add steel. Short of bending capacity, add cover plates to the flanges. Short of shear, thicken the web, add it in the wrong place, and you have bought weight that does nothing. Now the designation ISMB 400 at 61.6 kilograms per meter is Indian standard. MEMB, medium weight beam 400, and here is the trap, that is the nominal depth in millimeters, not the width, not the mass, and 61.6 kilograms per meter is the mass of every meter you buy. Why write the mass at all? Because two sections can share a depth, an ISMB 400 and an ICE WB 400 are both 400 millimeters deep, and they are completely different sections. The mass is what tells them apart. The same logic runs everywhere. I say 100 by 100 by 8 is an equal angle, 100 millimeter legs, 8 millimeters thick. Look at the shape of a rolled section for a moment. Tapered flanges, a fillet at every junction. Calculating its moment of inertia by hand is long and it is inaccurate, so nobody does. Every rolled section made to Indian standards is tabulated in SP6, Part 1, the steel table. For every single section, it gives you the area, the moments of inertia about both axes, the radii of gyration, the section moduli, the mass per meter, and every dimension. You look them up. That is the whole point of it. And this matters more than it sounds. Steel design is not a shaping process, it is a selection process. You choose the lightest section whose tabulated properties satisfy the requirement. In most numerical questions, the first mark is simply for opening the table at the right row. One term has been doing a great deal of work in this lesson and it deserves a proper explanation. The radius of gyration, it is written r, and it is simply the square root of I over a moment of inertia divided by area square rooted. It has the units of a length millimeters, and here is what it actually measures. It is the distance from the axis at which you could imagine the whole area gathered into a thin ring and still get exactly the same moment of inertia. So in plain words, r tells you how far the material sits from the axis. A large R means the area is spread well out. A small r means it is bunched in close. Every section has two of them, Rz about the strong axis and Ry about the weak one. And here is why it decides everything in compression. The slenderness ratio is lambda equals KL over R. The radius of gyration sits in the denominator. So a small r gives a large slenderness, and a large slenderness means a weak column, which is exactly why the smallest radius of gyration is the one that governs. Here is a rule that decides more steel design than any other. A compression member always fails about its smallest radius of gyration. Think about what that does to an I section. It is strong about Z, and weak about Y, and the column will always buckle about the weak one. So all that strong axis capacity is simply wasted. Now a tube, its radius of gyration is the same in every direction. There is no weak axis to fail about. Nothing is idle. Let me show you what that is worth. Take a solid round bar 100 millimeters across and take a hollow tube 150 outside, 111.8 inside. Both have exactly the same area of steel, 7,854 square millimeters, identical weight per meter. The solid bar has a radius of gyration of 25 millimeters, the tube 46.8. Now the Euler buckling load is pi squared EI over L squared, and I is AR squared, same area, same length, same steel, so the load depends on R squared and nothing else. 46.8 over 25 is 1.87, square it, 3.5. The tube carries about 3.5 times the load. For exactly the same weight of steel, push the material out to the rim and it works. Bunch it at the center and it idles. That is the entire argument for tubular struts and tubular trusses. Against it, the connections are harder. The inside cannot be painted, so the ends must be sealed, and it costs more per ton. Steel design is not governed by one code, it is a family, and knowing which code answers which question is itself an examination question. IS 800 2007 answers how do I design it? It is the design code. IS 875 parts 1 to 5 answers what loads act on it, dead, imposed, wind, snow and special loads. IS 2062 answers what steel is it? The grades. SP6 Part 1 answers what are the section's properties, the steel table, is 1161 for steel tubes, is 4923 for square and rectangular hollow sections, S816 for welding and IS 1367 and 1363 for bolts and nuts. One habit worth building, always write the year with the code. IS 800 is incomplete. S 800 2007 is an answer because that revision is what moved Indian steel design from working stress to limit state. So back to the two questions we started with. What steel is this? Its grade from S2062 E250 for ordinary structural work, yield 250, ultimate 410. And remember, it weakens as it thickens. What shape is it? Its section from the steel table is MB 400 and the number is the depth. Hold on to three things and this whole lesson stays with you. The lower yield point is the design value. The modulus of elasticity never changes with grade. And a strut fails about its smallest radius of gyration, which is why a tube beats an I section every time. The study notes and the model answers for this topic are on the Telegram channel, free to download. In the next piece, we start classifying sections and we meet limit state design properly.